Well, thank you very much for this invitation. So most of the work I will discuss this morning is due to Margaret Bilu and can be found in her PhD thesis. And the question, the topic is a geometric analog of a question in number theory. Namely, counting points of bounded height in algebraic varieties. Over number fields. So to be specific, let's take a variety X in Pn, defined over the rationals, just to be simple. And define the height of a point for X, a rational point. And the height is just the maximum of the absolute values of the homogeneous coordinates, provided that the coordinates xj are taken to be integer and coprime. And then the question is, what can you say about the function of a variable b, n of b, which is just the number of points, rational points of x, whose height is smaller than b, when b goes to infinity. And the general expectation is that it grows like a constant times a power of b times a power of log b. And in every example where something is known about that problem, this is what happens. And so let me give two examples. The first one is due to Chanuel. I think it was published in 1979, but it's probably older by 1 or 2 decades. Is a case where X is a projective space itself. And then what happens is that, so if you take, let's write nx of b, and Pn of b is roughly 2 to the n divided by the Riemann zeta function at n plus 1 times b to the n plus 1. And the second example will be a product of two projective lines embedded in P3 via the Segre embedding. So the image is just the hypersurface xy equals zt. And then I think n of b is a constant, which I do not remember, and I did not take the time to compute it yesterday night, but it's b times log b, and some constant which I do not remember. So this question had been put forward by Manin and his collaborators, Batirev, Franke, Chinkel, around 1989. And the main case to be studied is the case where X is a Fano variety. So Fano means for us that X is smooth, and anti-canonical line bundle is ample. And just to be concrete, it means that X can be embedded in Pn, and with a top differential form omega. So if X has the dimension D, omega would be a D form. And you assume that the divisor of omega is just a multiple, a negative multiple. So minus D of omega is just a positive multiple of a hyperplane section. So for example, if you take X is a hypersurface of degree, so if D is a dimension, let's say delta, let's say capital. Sorry? Depends what you mean by multiple, rational multiple. Yeah, up to a constant, but just a positive. It's just. Yes, if you wish to. So then, if it's an hypersurface of degree D, the condition is just that D is strictly smaller than n plus 1. And there are also a lot of difficulties. So let me just say about this condition. In number theory, it is believed that the behavior of rational points is governed by precisely this class. And that this class can be roughly either positive or negative. In fact, it can be something in the middle, but let's forget about that. And in the, say, when the anti-canonical line model is positive, this is this case of Fano varieties, where people expect that the variety will have many rational points. And difficulties are to be quoted in a few minutes. And in the opposite case, where the canonical line model is positive, then people expect, for example, the conjecture of Lang predicts that the rational points will be located in finitely many strict varieties. So you have two opposite behaviors, where there is a lot of rational points, which is this case, and the other, which belongs to model conjecture and generalization of it, where you expect that there are few rational points, or that they live in sparse in varieties. So the difficulties is that one needs to assume that the rational points are Zariski dense. This is mainly because one expects a geometric answer to the above question, that to give a geometric interpretation of the constants A, B, and something which is of more arithmetic nature of the constant C. And if the rational points are not Zariski dense, it is quite unreasonable to expect a global interpretation of the behavior of rational points. The second difficulty is that one needs to restrict counting problem to appropriate open subsets. So Zariski open subsets. This is necessary because it was observed from the beginning of this story on that in some cases, for example, if you take the plane and you blow up one point, so you are just in some sense adding a line to the plane, and then if you count the points of the line that you've just constructed, then you have more rational points that with what is predicted by the conjecture. So people said, okay, remove the line and count outside of it, and then it was observed that the behavior is more or less as expected. So one needs to restrict the counting problem, and there is, up to now, there is no general what this appropriate open subset should be. And in fact, I will say more about it now, because the final main difficulty is that there are counterexamples. And so in some cases, one needs to remove not only a closed subset, but a subset in the sense of Hilbert's irreducibility theorem. And counterexamples are due to Batirev-Schinkel and Leroy-Dullier. Okay. No, for P1 times P1 is okay. I mean, you can count points on. No, because okay, so that's a good question. But the problem change the birational class, you change the problem. It depends not only on, it depends on really on the way the variety is embedded. Open subset, but if you remain its natural embedding, then the problem is okay. For example, so the counting problems for P2, P1 times P1, or P2 blown up on a point, they look similar because birationally the same varieties, but they are very different and with different outcomes. So in any case, there are many examples. First of all, the circle method of Hardy and Littlewood. And refined by Birch in the 60s, allows to treat the case of hypersurfaces of small degrees compared to the dimension. So for example, n has to be 2 to the d or something like that. So a lot of people in the 90s and beginning of the century have studied Del Pezzo surfaces, for example, de la Bretèche, Browning, and so on. Well, the general case of a Del Pezzo surface is still open, but many cases have been given. An important case is given by flag varieties. So, for example, usual flag varieties or generalized flag varieties, quotient of a reductive group by a parabolic subgroup. For example, quadrics in any dimension. And this case is due to Franke, Manin, and Schinkel. But relying crucially on the work of Langlands on Eisenstein series. And the last case to be quoted is toric varieties, or more generally, equivariant compactification of some groups. And for groups, you could take vector groups or semi-simple groups. And still some nilpotent groups. And then it's due to, so toric varieties, it's a theorem of Batirev and Schinkel. Vector groups is Schinkel and myself. Semi-simple groups is Shalaika, Schinkel, and Taklo-Big-Hash. And independently, Grothendieck and O, nilpotent group, I think it's Shalaika and Schinkel. So the the geometric analog I promised you is the question of what happens if you want to replace Q, the field of rational number, by the field of functions of a curve, say projective and smooth and connected, C. So the field of functions will be K of C over a base field K. So then the first case that comes to mind is the case where the field, the ground field K is finite. Then the story is very similar because you still can count the points of bounded height in this context. And so there is a similar counting problem. But the theory is not as well developed, but I think in case of flag varieties or toric varieties, it has been done. Flag varieties is because of the work of Morris on Eisenstein series over function fields, and Emmanuel Père did what Franke, Manin, and Schinkel have done. And a case of toric varieties is due to Burki. Vector groups is not proven because we use resolution of singularities, so it doesn't work in positive characteristic. And same for the rest. So, but the question is what happens when K is algebraically closed? So maybe just to say, if you take here I've written the definition of the height in the case of a rational number. So let's take for the field of polynomial or rational functions in one indeterminate. So F, and then the height of a point just be the maximum of the degrees of polynomial P naught Pn, where X is the point of homogeneous coordinates, where the polynomial, where Pj are polynomials, and coprime. And then, so you can see that if you are over a finite field, you have only finitely many such families of polynomials. You just count the possible coefficients in degree 0, 1, 2, and b, and you take care of coprimality and so on. But at least the finiteness property is assured, and that's all. But if k is infinite, then you have an infinite number of such families of polynomials, and you cannot count in a usual way. But what you can observe is, for example, in this case, the families, such families, form a constructible set. I mean, it's just defined by, it's in some sense up to the coprimality conditions, but it's in some sense an affine space because you chose coefficients one by one. So, in general, so the set of rational points over F with height smaller than b has a natural structure of, in that case, it's an algebraic set. And, sorry, over, yeah, exactly, over K. And so the question is, how do this, so let's write this mxb. I'm going to write d, if you know. G. And so the question is, how do they behave when d varies? Sorry?
Is it, so I think we have to consider the categorical constructible set is constructible by ejections.
Well, let me say something else. In this case, MG is just is constructed by Grothendieck. It's just is a Hilbert scheme of morphisms from epsilon x from C to x. So x, remember that it's embedded in Pn, and the degree so then you have a precise definition. And this MG has been constructed by Grothendieck. So how do they behave? The question is, what are their dimensions? Can one understand the number of irreducible components, or, if possible, the cohomology, the Hodge-Deligne polynomials, whatever geometric invariance you could be interested in. And the way these spaces are studied is similar to the way the number of points of bounded height was studied in the arithmetic case, namely by introducing a height zeta function. So in the arithmetic case, this is just a Dirichlet series, zeta x of s, which is the sum over all rational points of the height of x to the power minus s, and s is a complex parameter, and the real part large enough so that the series converges. Yeah?
The definition of MD in C is arbitrary curve, which is one.
Sorry?
The definition of MD is epsilon x is important from C.
Yeah, because this is this curve. No, but then it's you can, okay, like it's a space of morphisms, but it's also constructed by Grothendieck, because you can view it as sections of x times C to C. Well, it's. If you wish, but you can also construct morphisms.
K-morphism from C.
Yeah.
X is a scheme over F, and C is a scheme.
X, no, X. Oh, okay, yeah, okay. In that case, okay, because I was. You're right, okay. So you're right, okay. So let me give the precise definition when I state a theorem.
Is X a variety of a little k generally?
Sorry?
Is X a variety of little k?
No, that was exactly what Gaber was pointing out. In general, X is something over F, but I want to say that in 5 minutes, not now. And so the Motivic height zeta function is just the sum where and this is a formal power series in the Grothendieck group with coefficients in the Grothendieck group of varieties. So K0 over K. Is a Grothendieck ring of is generated by as a group by of K varieties. For MG, I take equals to T, so it's just a just a matter of convolution. And the relations in this group are just that a class of X is a class of F, no, not F, Z, plus a class of X minus Z, where Z is a closed subscheme. And the ring structure is the one you imagine, that namely the product of two classes is just the class of the product. So despite its easy definition, that is a fairly complicated ring.
Varieties are reduced.
No, don't need scheme of finite type. So the variety has the same class as its reduction. Okay. So now let's be more specific, and I will state a theorem, but maybe I will change the blackboard because the context needs. No, that's okay. So the text of the theorem of Margaret Bilu. So F will be a field of functions of a projective smooth connected curve over an algebraically closed field. K will be algebraically closed and characteristic 0. She considers a projective smooth variety over K and a morphism a non-constant morphism, a flat morphism from X to C, and a line bubble L on X. And so she makes hypothesis on the generic fiber of this. So she writes generic fiber, the variety over the field F is just denoted by capital X. L will be the line bubble L related to XF. And the assumption is that so one assumes that X is an equivariant compactification of an additive group, of a vector group. So G, which is isomorphic to some GAN over F. And this means, just to be clear, that G is viewed as an open subset of X, and you have the multiplication or the addition from G to G, G times G to G, and it extends to an action from G, an action of G on X. So the second hypothesis, okay, is that if you look at the complement of this open subset G in X, it has to be a divisor with normal crossing, with strict normal crossing. In more elementary terms, it means that it's a union of smooth hypersurfaces and they meet transversally. And the last assumption is that the class of the line bundle L is the anti-canonical class of X. And it's fairly easy to produce examples of this kind. You have the case of where, for example, if X is a projective space with the action of the affine space complement of hypersurface at infinity, but you can also start from this example and blow up something at infinity and produce many new examples.
You want L to be a pair of
No, it's not ample, in fact. Not necessary. It's not necessarily ample, but it's big enough.
Because of the other assumptions?
Yeah, because it's only big. It's slightly less than ample. But you are going to prompt a question by Forgaber in 2 minutes. But I have prepared that question. So you already asked it, but so now for every integer d, one can consider the set of, say, a section from C to curly X, section of pi, such that, first of all, the degree of epsilon upper star L is G, so this is a height condition. And one more condition, one assumes that the image of epsilon is not contained, so one assumes that the image meets the open subset G. So in this problem, one completely removes the points which are located on the boundary divisor x minus G. And this is important because in that case, first proposition is that MG is naturally a constructible set, a K-constructible set. And in fact, if the line model L were effective, it would be an algebraic set. So one needs to, for the counting problem, because the line model L is not necessarily ample, one needs to remove some points at infinity. And the bigness condition assures that this MG is something constructible. And also MG is empty for D negative enough. And so the zeta function is just the sum for all D in Z, class of MD, T to the D. So it lies in the K0 var K, the ring of power series with coefficients in K0 var K. And because some MG for negative D could be non-empty, one needs to inverse to invert T. That's not a serious issue. And so the main result of Margaret Bilu's PhD thesis is that one assumes so one is interested in spaces of such sections. So for these spaces to be non-empty, there is an obvious necessary condition of a Hasse principal type. I mean, you need to assume that for every that there are local sections, local in the sense of completion. So one assumes that for every close point x in X, the set of sections in C, the set of sections of pi over this completed local ring is non-empty. Otherwise, you have nothing to count. So then, there is an integer A, at least one, such that if you take the zeta function, Motivic zeta function, so z of t, and you multiply it by L minus LATA to the power R, and I did not define what R is. R is a rank of the Picard group of capital X. And so if you make this product, and L is the class of the affine line, as usual, if you take this product, you still get a series of this kind, but then this series converges where t is small enough. So, and there is also delta positive for if t is smaller than L minus 1 plus delta. And takes a an effective non-zero value where t is L minus 1. So saying that a series with coefficients in these Motivic rings converges for such elements mean that if you plug it formally t equals L minus 1 plus delta, you get a series and you claim that the coefficients go to 0. So there are natural topologies on ring like K0 over K and the same ring when you invert the affine line. And the first topology that had been used in Motivic integration was a dimension topology. So you say that this is something of the form a class of variety divided by power of affine line is small if its dimension is very negative. And L is a class of affine line. Yeah? It's an absolute value of t. It means that if you plug formally L minus 1 plus delta, you get something which is small. Small because there are topologies on Grothendieck group of varieties by the dimension topologies. You say that something which is, yes, it is. Yeah, in fact, it is a very serious issue on this work, so I need to explain it.
By big X, you mean the geometric?
No, big X over the curve, over the function field of the curve. Exactly what is written there. So,
delta is an integer.
sorry?
Delta in this inequality is an integer? L minus 1.
Delta? No, delta will be a small rational number. No, but yeah, it means that, okay, let's say about topology. But, no, wait a minute before I discuss the topology, okay? But in principle, you could say that, but not quite. You take a series sum of AD t to the d, you say that converges at t equals L minus whatever, minus alpha, if dimension of AD minus alpha d goes to minus infinity. And the dimension, just here, it's assume that AD is a class of a variety. So you have a filtration on the Grothendieck ring of varieties, and you assume that it is and the actual definition involves weights, but I want to talk later about that, but I have only 10 minutes to be later, so. And before that, I want to give a corollary. And so the corollary is as follows. For every integer p between 0 and n minus 1, when when d goes to infinity in the class of P modulo A. So two things can happen. Either the supremum limit of dimension of MD divided by D is strictly smaller than 1, or dimension of MD minus D is eventually constant. And if you look at so kappa of D, kappa of MD, kappa of MD is just a number of irreducible components of maximal dimension. So this log of kappa of MD divided by log of D goes to some number, say E, which is in between 0 and R minus 1. And moreover, the second case happens at least once.
You mean at least for one class?
Yeah. So the issue is that, for example, the class L, curly L, could be a multiple of 2. And then when you look at all the grids, they will all would be multiples of 2. And so the spaces MD would be empty for odd D and possibly non-empty for even D. So one needs to take care about this. So this is the issue about the small number, the integer A, and the necessity of this disjunction. And I won't write it on the blackboard, but more generally, what the result says is that if you look at the Hodge-Deligne polynomial of MD, in that case, you control a positive proportion of the top part of this polynomial in two variables. So the Hodge-Deligne, I mean, or you control the positive proportion of the Hodge structure of the virtual Hodge structure of MD. Okay, so I have five minutes to quote. So the proof is inspired by the proof of a similar theorem in number theory, which I had done with Yuri-Chinkel in 2000, roughly. And it begins that way. You take, so now it's the usual high zeta function, sum over all rational points of G, height of x to the power minus s. And then what you do is you write the height as a product of local components. So you use the fact that you're only considering points on G to explicitly decompose the height, which was at the beginning a maximum of some absolute values of integers, but now you separate the p-adic contributions of all this. And now you view as this formula as a sum of the values on a discrete group G of Q of a function which lies naturally on the adels of Q. So then this is a function on G of A and AQ, which is the adels. And you sum over discrete compact subgroups, and then you can apply the Poisson formula. And this formula transforms this sum to a sum over some characters of the adelic group, which are trivial on the subgroup there, of the products of all V of the Fourier transform, the V-adic Fourier transform of the functions hv to the minus s computed at the character xi. And so this is the analog of the Poisson formula that says that if you have a function and so this is the Fourier transform, and the 200th anniversary of Fourier's death is this year, so we have to celebrate that. So this is just the analog of this Poisson formula. And so now the main term, the Fourier transform as kind of magic to allow you to view phenomena on the spectral side, which are invisible on the geometric side. And then on the spectral side, which is there, the main term is for the trivial character, xi is 0. And so you look at this term and you understand it precisely, because then all these functions are just integrals of height to the minus s. But this is a very standard function in p-adic function theory, because it's a kind of Igusa zeta function. So then you get Igusa zeta function. And for HV, and you get an Euler product of Igusa zeta functions, which you have to understand. Okay, now, and then you also need to study the terms for xi 0, but say they belong to the remainder term, and that's okay. So now the goal is to copy that in the geometric setting. And so now this is done by two, maybe I will erase that. No, just. So in the Motivic setting, one needs first Euler products. One needs a Poisson formation. Summation formula. No. And one needs to take care of topology. Because the reasons for which these Euler products converge is not strictly explained by dimension, but it's explained by weights. So one needs to refine the topology, as I hinted before. So what allowed Margaret to start her work is that, at least in a simpler case, the Poisson summation formula had been studied by and proposed by Gruszowski and Hodge-Deligne. And indeed, François Lezer and I took the opportunity of this formula to prove a similar result as Margaret's one, but where we restrict the counting problem to a much simpler one. And then we were able to make use of this formula to copy the strategy of a number field and to count some varieties. But the main point of our thesis is to construct Euler products, because in Gruszowski and Hodge-Deligne theory, there are only finitely many places that appear at the same time. And here it's very important that all places appear. And so she has a full definition of objects of this form. Take a variety X and take a class of the form Fy of t, which is just sum of Yj Tj, so where Yj is some variety over X, and Y0 is just X is identity. And so she defines products for all X in X, Fyx of t. So it's a kind of Euler product of series with coefficients in Grothendieck rings. So this belongs to K0 Grothendieck rings relative to big X, and this will belong to K0 over K. And the definition she gives, and then I will stop. So the defined using symmetric products and a lot of combinatorial work. But for example, when she takes, if you take for Fy of t is just sum of t to the j, so it means that the class Yj is just x and it's just identity. You take this series, sum of t to the j, which is 1 divided by 1 minus t. Then what she obtained is that product for all x of 1 of 1 minus t is just the Kaplanov zeta function of x, namely the sum over all n of the nth symmetric product of x t to the n. And a formula which is reminiscent to the formula product for 1 minus, say, q minus well, which is reminiscent of the formula product of 1 minus of the Riemann zeta function as a product, Euler product, with a similar formula, 1 minus t degree of x, which would be the zeta function of x in the case of. So she has a definition. It's not necessary for me to write it on the blackboard now, but and that allows her to recover this Kaplanov zeta function and which works perfectly, which has enough properties so that she can conduct the harmonic analysis proof, and she got her thesis that way. So that's a nice work. So I'm glad to have been able to report on it. Thank you.